My name is Caio Vilela. I'm an engineer in the Platforms Group, and it's my pleasure to introduce you to John Davis from Deeya Energy. He's going to talk about flow batteries, which I think is an incredibly promising technology for energy storage. So with you, here's John.
Hi there, my name is John Davis, and I am the Vice President of Business Development for Deeya Energy. And what we're going to discuss today is flow battery technology. It's an energy storage platform and brand new technology that is a game changer in the way that both grid generated and non-grid generated energy can be utilized more efficiently. And so I have a number of slides. The presentation, it's about 45 minutes long. So then we'll, answer your questions as we go through after we finish the presentation. So let's do an introduction to Deeya Energy. Deeya was founded in 2006, and we're here in the heart of Silicon Valley in Fremont. We're based in Fremont. We have developed a technology that was originally researched by NASA in the 1970s. NASA certainly had a distinct interest in energy storage for long-haul space missions, and this type of chemistry that our battery is based out of was initially explored by and researched by NASA in the 70s. It's called a redox flow battery, and it is based on an iron chromium chemistry that is dissolved in hydrochloric acid. Deeya's mission is to develop the technology into applications that are, that make a difference in allowing energy to be much more efficient. So we are developing our products for energy storage and management solutions that focus on industrial and consumer applications, similar to some of which are telecommunications and, of course, data center backup power type of applications. We want to be able to maximize the utilization of power at various generation capacities. And one of the applications you'll see me discuss is off-grid power and how we can better utilize the use of genset and renewable energies for use and make it much more reliable. And by doing this, for mission critical applications, by using energy storage, we can significantly reduce the expense of on-site generation. The battery is extremely environmentally friendly, no heavy metals, nothing that will harm the environment. And of course, we are very excited about the technological breakthrough that Deeya has come up with this technology. Our company is a relatively new company. We're in startup mode. We're moving from startup to production. We have a handful of top-tier VC firms here locally that continue to fund our research and development and operations. And one of the new press releases that has just been made is that we have completed a $30 million Series C fundraising event that is pushing us towards very quickly towards commercialization. So what is a flow battery? Well, a flow battery is a type of electrically rechargeable battery of which the energy is stored chemically in a liquid electrolyte. And unlike conventional batteries that are stored, the reactive materials are actually dissolved metals in the electrolyte. So the flow battery has a number of components involved to do that. It has tanks that in fact hold the reservoirs that hold the electrolyte with the metal that is immersed in it. And it has a series of pumps that moves the liquid through a cell stack. Now the cell stack is actually very similar to a fuel cell technology. It is a membrane-based cell stack. Sometimes it's uses even Nafion, which is the same as the hydrogen fuel cells. In our case, we have a little bit of a derivative of that. But what happens is that the ions will pass through the membranes of the cell stack, and electrons will flow from one side of one reservoir to the other side of the reservoir, and basically it will harness the differential, the voltage differential between the two reservoirs through the cell stack, using that as the engine. So it's kind of a hybrid between a fuel cell, and I like to call it a closed loop rechargeable fuel cell. It doesn't use any fuel. Like I said, it's electrically rechargeable. And so it's in between a battery technology and a fuel cell technology. Why this makes this very interesting and usable is that this type of technology can be charged and discharged literally many, many thousands of times without any degradation or ill effect on the system at all. So unlike conventional battery technologies where for example, lead acid systems require you to have to replate the lead each time you charge the system. There's no mechanical element to the battery that requires that type of activity. So the ability for the system to charge and discharge many, many thousands of times becomes much more available for you. So our system is basically like I said, it's a green technology using iron and chromium with hydrochloric acid as the electrolyte. It's packaged in a small package that looks similar to about the size of a refrigerator. So you basically have two tanks that are in this particular outdoor enclosure, and you have a cell stack that is placed on top of the tanks. And the other two components are two pumps, one of which for each reservoir that moves the electrolyte through the cell stack, and then basic electronics that takes the raw DC voltage that's generated from the system and converts it and conditions it to some sort of usable voltage that can be anywhere from 12 to 96 volts DC. So basically, as I've mentioned, the components involved are that the electrolyte, there's two different reservoirs, of which both reservoirs have exactly the same chemistry and same liquid. The difference is that what happens is that the metals will move through different valence states. So one side of the system will have the metals become much more positively charged than the other reservoir, and there will be a voltage potential between the two reservoirs of about 1.5 volts. So if you have that on a large scale, what happens is the cell stack acts as an amplifier and allows you to generate a large quantity of current when you move the two electrolytes through the cell stack, thus giving you a usable power generation source. So the differences between our technology and incumbent lead-acid battery technology is that traditionally lead-acid batteries, which have a very long history, over 100 years of development, and literally have been in the same type of chemistry for that same time, have very little usability after you discharge the system at approximately 25%. You can go below the 25% discharge cycling capacity for lead acids, but what happens is it always will damage the battery and cause the battery to not be able to charge back to the rate that you originally had when the battery was first new and usable. So one of the issues that you have with lead acid batteries, specifically in a backup power type of application, is obviously it always continues to degrade and lose its capacity over time. The more you use the battery, the faster it degrades. With our technology, we've gotten past that issue, and we now have the capacity of charging many, many, many thousands of times with no degradation of its performance over time. So what that means is we can use the full scale of the battery for usable energy storage. And that opens up a lot of brand new applications that now traditional energy storage systems would not be able to satisfy. And so by developing a system that has the ability to move through its cycles many, many thousands of times, you now have the capacity of using a daily cycling system for various applications like storing solar energy on a daily basis, or working on a system that's off the grid, that's running off a diesel generator, and being able to turn the generator off for many hours during the day and using your stored energy as your primary source of power. So the ideal energy storage product is that it needs to be insensitive to temperature, which lead-acid batteries are not. They have they're affected by both very cold weather and by very warm temperatures. They need to have the capacity of being fast charged. So the ideal situation is that you can charge the battery as quickly as you discharge the battery. Again, lead-acid batteries do not have that capacity. As you move through time and lead acids are charged over and over and again, it takes much more energy to get the battery back to its state of usable storage, up to approximately 5-to-1 charge to discharge ratio. If you had the ability to do infinite cycle life, so every day being able to cycle the system time and time again with no degradation in performance, is obviously a huge benefit. Being able to charge the system efficiently, trying to have the system where you put back the energy in the same capacity that you have as you use, as opposed to having a large quantity of energy you have to put back into the battery just to get it back to where it originally was, would be a great benefit. And of course, being able to have no hazardous materials in the battery would be fantastic. Of course, lead-acid batteries traditionally have had the environmental issue of disposability for lead. Obviously, you can recycle lead acids, but in many parts of the world, that just doesn't seem to happen. So here is a graph of a traditional lead-acid battery in a high cyclic application. In this particular case, we have used a diesel generator in an off-grid application, a telecom application, where the battery is being charged on a daily basis. And of course, the graph in the middle shows the result of charging and discharging a lead-acid battery over time. Traditionally, you'll see that the graph shows that the capacity of the battery begins to lose capacity immediately after each discharge cycle, to a point of not being able to have a usable charge associated with the battery at any given time. Again, with our technology, our goal and what we're able to do is have that high cyclic capacity where it has the ability to charge and discharge at exactly the same rate to the same maximum charge ratio each and every time, well over 10,000 cycles. So in what applications would in fact could you use high cyclic energy storage? Well, Deeya has focused a number of applications, for example, on very remote sites that would be similar to like telecom sites. Everyone knows that telecommunication sites have the need for backup power. In the U.S. and North America, the use of lead-acid batteries at telecommunication sites are basically an insurance policy in the case that you lose power on a infrequent basis. But on sites throughout the world, the telephone industry is exploding in places like India and Africa, Latin America. And a lot of these sites are actually off-grid sites. The ability to run the site off-grid and pay $20,000+ in diesel fuel at a specific site is very cost-effective at these locations. So it is, believe it or not, there are literally hundreds and thousands of sites throughout the world that are running telecommunications base stations off of diesel generators 24 hours, 7 days a week. So one of our major applications that we have pushed towards is taking the high cyclic capacity of our battery and working with the diesel generator on these types of sites, storing the excessive energy that a diesel genset generates, because the diesel gensets are extremely inefficient. They throw a lot of wasted energy away in heat, and then turning the generator off for as much as 12 hours a day. And the cost of fuel savings at these types of sites by running off of the battery 12 hours a day pays for the battery in literally a year to 2 years. So the return on investment is very high. And of course, if you mixed that with renewable energy, if you took solar and wind, and of course have these mission critical types of applications where you use the battery for storing whatever excessive energy is being generated by either solar or wind and the diesel genset, or allow the battery to smooth the effect of the inconsistency of renewables, then of course your power system becomes much more reliable. And in the case that, for example, in the case of using this as a traditional backup power for a UPS system, the battery system looks like a lead acid battery. It operates exactly the same. There is no differential to any of your infrastructure as to whether this is a lead acid system or a flow battery technology. The difference is that the level of reliability that the flow battery gives you for allowing you to not have to ever replace your battery systems again is paramount. So of course, our company has focused significantly on a number of very remote applications and sites. We have pushed very diligently into the telecommunications arena in India and Africa, and of course in the US and Canada and other places of the world. We still can compete with the incumbent technologies of lead acid and other technologies in the traditional use of batteries, and again, like I said, allow your systems to have much more reliability by using the technology that basically does not degrade. So this is what our system looks like. This is our first product. It's a 2.5 kilowatt system, and it has the capacity of giving you 24 kilowatt hours of energy delivery each day. So that means that it will have the ability to discharge 4 hours each discharge cycle. It operates at a very wide temperature range, down to -5 degrees up to 50 degrees C, without any ill effect on the battery whatsoever. It has a very high fast charge rate, so it actually can charge faster than it can discharge, which makes it very good for these high cyclic applications. So for example, if you have an outage if you had a system that was a UPS based system and you had a 4-hour outage, the battery can cover that outage very easily, and then would only take 2 hours to recharge itself to get the system back to a place where it's 100% ready to go the next outage. Of course, you can discharge the battery completely to zero. No energy, where there's no more energy storage at all, but it has no ill effect on the battery whatsoever. So again, that's a very high value feature. We're offering, because of the reliability of the system, we offer a 5-year warranty of the system. Also, I should mention that the battery can be designed to support various voltage ranges that are, very standard ranges for both telecommunications and UPS applications. The electrolyte at the end of the life of the system is reusable and recyclable. So we can take the electrolyte, we can remove the core elements of the system, which are basically chromium and iron, and then reuse the system for, and rebuild the electrolyte for use at a later date. So the electrolyte does not have, it basically has an infinite life for the electrolyte itself. It's not flammable. There's no emissions that the system puts out. There's no hydrogen emissions. So it's, again, a very safe, benign technology that can, in fact, be used indoors. Our product roadmap is that we have started with a 2.5 kilowatt small package, again focused a lot on the cellular tower networks that are throughout the world. We are designing, and our next step will be a 5 kilowatt package, which will be in a little bit larger outdoor enclosure. Our plan is that the systems, in fact, and the technology is very scalable. By adding more electrolyte, you add more energy storage. By building the cell stacks or ganging cell stacks together, you add more power. So because of the system being as modular as it is, we have now the ability to scale up the technology product-wise to allow us to build systems that are much more larger in scale and opening up the use of this same technology for many, many other applications, including grid applications, wind and solar on a larger scale, many other applications on for telecommunications and other UPS-based situations. Basically, it's a very simple machine. There are 4 components to the machine that make the system operate. The intellectual property that we have developed is based on our cell stack. It's, like I mentioned before, it's a basic cell stack design similar to the fuel cell industry, and it basically handles the conversion of as the electrolyte flows through the various cells in the stack. It basically transports ions through a membrane and allowing power to be generated at the cell stack level. The next component of the system is the pumps. So we basically pump a liquid through the cell stack. So that's a very well-known technology. Pumps are off the shelf, and so it's not an unreliable part of the system. And the third part of the system is the electrolyte itself, which is just basic hydrochloric acid with our salts that are immersed in the system. And the fourth is the electronics that are used to convert the DC system to from raw DC to usable DC. I got a question. I'm sorry? Good question. The concentration of the hydrochloric acid is 1/5 that of Clorox. So it's mostly water, a very diluted solution. If you look at various graphs of how our system compares to incumbent lead-acid technologies, again, what you see is that there is no other technology out there that has the ability to give you a flat line discharge curve over a very long period of use and allow you to have the same amount of energy storage at cycle number 10,000 as opposed to cycle number 1. Lead acids do not do that. The other problem is that lead acids are directly affected by higher temperatures. So most of the time, as you are well aware, and probably your data centers, you have a large scale of lead acid batteries used for UPS applications that you have to condition, and you have to use in an air-conditioned environment, which takes energy itself to allow the batteries to attempt to have some level of life cycle that you get the most amount of investment from money from use out of that particular investment. So our system basically allows you to not only have the long life cycle, but not have to be concerned with the environmental issues of conditioning the temperature of the battery to make it work and operate properly. So again, one of the applications that I'm sure that will be of interest to Google will be a data center UPS use. And I was inquiring a little bit about the use of your lead acids earlier, and the use of being able to, whether or not you're using lead acids in UPS applications in parts of the world that potentially do not have reliable grid applications. Those are the sites that you're going to be replacing lead acids much more readily than sites like here in this facility, where your grid is very consistent and have very few outages. But if you have these types of sites where you're running your UPS quite a bit and you're having to turn diesel gensets on to cover the outages on long-term scale, the Deeya system will allow you to number one, reduce the amount of money spent on energy storage because it's a one-time CapEx expense for a long period of time, and also to reduce the amount of potential diesel fuel that you potentially would have to have on site and run, and having to run a diesel generator as an augmentation in the case that you're losing power for a much longer period of time. So there's a lot of ancillary benefits to having a system that gives you 4 hours or plus runtime at a battery, as opposed to having a much smaller battery system that you're having to bridge to a generator to keep your data centers up and running. And again, obviously, everyone is very interested and excited about renewable energy. Google is on the forefront of that, and this platform now allows you to have inconsistent renewable energy be able to be much more smooth and consistent for the use for data sites or other types of applications throughout Google's infrastructure. So by using this on a daily basis and smoothing the wind, or capturing solar in the daytime and then using the battery at night for delivery of power to mission critical applications, is now a very doable application. So today, we are located, Deeya is located in Fremont. Our headquarters is right across the bay. We also have developed a manufacturing facility in India, and we are making systems and delivering systems worldwide from both our locations here in Fremont as well as in India. And with that, that's my presentation. I hope that I've been able to share a little bit more information with you about flow battery technology, and if you've got questions, I'm happy to answer.
I have a few. I'd like to know more about the flow that's used, and if you have any leakage issues, or the regulation of that,
Right. Good question. The question is, Is there concern about if there is a leakage? If there's, obviously our system has chromium in it. It also has, basically it's an iron chromium alloy. So the difference is that the amount of chromium in the system as opposed to iron is very low. There is really no issue with the system. If there is a major leakage, that would be worst case scenario. You're looking at basically the needing to dilute the hydrochloric acid. And that's typically the big issue. All of our systems have secondary and third containment. So if there is some sort of leakage, we sense that immediately. The system will completely shut down, will limit the amount of leakage that occurs, and contain the leakage within our cabinet works. We mitigate that as much as possible.
And then you mentioned that the not needing to replace it with a kind of 12-year lifespan.
Yes.
So kind of how do you refresh the system?
Good question. The question is, what will be needed to refresh the system, or after the end of life? Basically, what we see is that the cell stack needs to be replaced. The electrolyte doesn't necessarily see much effect on the electrolyte. The pumps potentially might need to be replaced, but because the system is a machine, it's serviceable and has the ability to be restored by having new components put in the machine very easily. Right now, we are measuring a round-trip efficiency of about 72% at the DC level. Obviously, by putting a system on an AC inversion, you lose a little bit more efficiency, but the DC to DC charge ratio and the efficiencies of our system are extremely high, 68 to 72%, and that's measured again after quite a number of cycles, throughout its life cycle. So that is very consistent.
So that's what roughly between charging and discharging?
I'm sorry, say it again?
That's split equally between charging and discharging?
That's the round trip efficiency of.
Well, yeah, I know, but
Yes.
Separately,
Well, most of the loss of efficiency is during the charge cycle. The discharge cycle is probably much more higher efficient than the charge cycle, and most of that is based on converting. Is lost in electronics, and we lose quite a bit of some level of energy in converting to a level of voltage that the system needs to have to push energy back into the system, as opposed for it naturally wanting to come out. Like any energy storage system, it wants to deliver, and so discharging becomes a very easy natural thing for any energy storage system. So putting energy into the system is less efficient than the delivery of the energy. Let's see, I had one back here. Let me get this guy back here. That's a great question. The question is, if you charge it and put it in an idle state, does it have any loss of energy over time? What we do is we turn valves off in the system that isolate the tanks from each other. So because of the system has various balance states in the metal, they don't change. That doesn't change. So as long as there is no path for leakage current between the tanks, then it will stay in that state indefinitely. So the question is, I'm going to convert that question to how much energy does it take for the machine to run itself? Less than 100 watts. So it's very, when we've rated the system 2.5 kilowatts, then that is the output of the system.
So if you discharge at the rate of 2.3 kilowatts, you have 4 hours. Now, do you maintain the efficiency versus if you were to use only half of the power, would you get twice the time at the same efficiency?
If you use half the power, yes, you have twice the amount of run time. So you have amount of energy storage, which is approximately 10 kilowatt hours. So if you're only discharging a kilowatt, you would have 10 hours of runtime. If you're discharging at 2 kilowatts, you would have approximately 4 or 5.
Efficiency
Is exactly the same.
So you're saying your accessible capacity is independent of your charge or your discharge?
That's correct. And the capacity is independent of power delivery, because what we've done is we've separated the electrolyte from the power system. Unlike a lead acid battery is one big block. So to scale that, you have to buy both power and energy in one block. So what we do is we've segregated that away from each other. So if we want to have more runtime, or if we need to build a system that has more runtime, we just need to add electrolyte. And so you have a 2.5 kilowatt system. Then if you need 10 hours of runtime, have bigger tanks with more electrolyte. If you need more power, you can increase the size or the number of cell stacks for delivery of power. Let me have this question here.
You're comparing to lead acid. Which technology of lead acid are you talking about? Flooding cells, spiral wound, or or ice plate? The latest technologies are actually
Absolutely. Some of the new technologies for lead acid. The question is, what are we comparing to as far as the basic technologies in lead acid? Most of our comparisons in our scales are VRLA technologies, not flooded, and most of which are aimed again at a telecommunications applications that we significantly push our value proposition towards. Back here in the back. Yes, there is. Well, there is comparison, but the application use is much different. We can't, this is a machine. We can't make a system that is in the package that a lithium-ion battery is. Lithium has an extremely high energy density, but the price you pay for that is that when you scale that up to multiple kilowatt range for applications other than maybe hybrids or that type of thing, it becomes extremely expensive and hard to manage. Lithium also has the issue with temperature and that type of thing. So,
I guess part B is there a vehicle application for your
the question is there a vehicle application? Not in the foreseeable future. We're still fairly low in energy density for vehicle applications. This machine, 2.5 kilowatts, probably weighs 2 tons. Failure of the system is the system has a lot of it's a smart system, so we have the capacity of monitoring the delivery of energy and how it's being delivered. It's not unlikely to have a small leak. It's not unlikely to have a cell stack to fail. Membrane might have a failure that would cause the electrolytes to leak into each other. It doesn't affect the electrolytes at all, but would require the cell stack to be replaced. So it's like any machine, there are a number of different failure points. What we don't see is we do not see failures of our pumps. We very rarely see failures of our electronics. We're building the system to be extremely reliable. And if operated in the conditions that we have set forth, the system should have a 10-year lifespan. Anything else? Yep.
What are your biggest challenges looking at your roadmap?
Great question. What's the biggest challenges of our roadmap? Our biggest challenges is that we are overwhelmed with interest in this type of technology for various applications that we want to be involved with. Obviously, starting a company, we focused on a very high value application of telecommunications with a small system. Our next step is to scale that into various applications that would be utility grid types of applications, which, you know, the telecommunications industry we're estimating is $2 billion opportunity a year, you know, capped out today in as far as battery technology is concerned. The utility market is screaming for energy storage, and with the development of smart grid technologies, being able to integrate renewables at the utility scale level for distributed generation, the need for reliable, high cyclable energy storage is paramount, and we certainly will be working towards supplying that solution.
Quick question on just what the cost per kilowatt hour is, just a rough thing, you know.
Yes.
About the flow battery, for instance, as energy storage for solar, wind, you know.
Right. The question that we get poses to us quite a bit is, how can I have one of these in my home? Is it going to be cheap enough, less expensive enough for me to have the ability to have this as an appliance? We would like to do that at some point in time. As a small company, we focused on high value applications that generate revenue for us, so we are able to go get the economies of scale. Today, we're selling our systems in this small package and competing with lead acids in the $12,000 to $15,000 range for a 2 kilowatt system. Sounds a little bit high, but as we move into larger scale systems, what we want to do is offer systems that are approximately $2,500 a kilowatt, and that means that we need to build systems in 100 to 250, 300, 400, 500 kilowatt size systems that are containerized. Thanks so much for allowing me to present to you guys today, and again, thanks for coming.